Hey everyone, sorry I can't be in class today. I'm gonna do a video of what we were supposed to do in class today, and then let me know if you have any questions next time I see you in class. So we're gonna start our unit on exponential and logarithmic functions. And before we do that, we're going to just do a quick review on how to solve exponential equations and look at exponential applications. But I just would like you to just squeeze this in the top right-hand corner of your paper. We've talked about exponent laws, but I just want to do a quick refresher of exponent laws. So if I have a base to the power of m, and I multiply it by the base to the power of n, it's going to become the base to the power of m plus n. So when we multiply, we should add our exponents. So, and this is something you already do, but for example, if I have 5 to the power of 7 times 5 to the power of 2, that's 9 5s being multiplied together, so it's 5 to the power of 9. Also, if I divide, so if I have b to the power of m divided by b to the power of n, just a reminder that that becomes b to the power of m minus n. When you divide, you should subtract your exponents. So for example, if I have 5 to the power of 9, divide that by 5 to the power of 2. 2 of those 5s will cancel out, and then I have 7 5s left over. And then lastly, if I have b to the power of m, all raised to the power of n, so this is a power to a power rule, this becomes b to the power of m minus n. So for example, if you have 5 to the power of 7, all raised to the power of 2, that means 5 to the power of 7 multiplied by 5 to the power of 7, which means that we've got 14 5s being multiplied together. I know I said lastly, but just one quick other note that's really important. If I have b to the power of negative m, it means it's 1 over b to the power of m. So if I have 5 to the power of negative 7, that's 1 over 5 to the power of 7. Okay, cool. So to solve an exponential equation, we want to get like bases, get bases that are alike. And we're going to use our rules to get the bases to be alike. Once we get like bases, then we can set exponents equal to each other. So let's do a few examples. This is review from last year, but let's do a few examples. So for example, right here, if I have 5 to the power of 2x equals 25, well, we know that 25 is equal to 5 to the power of 2. So here we can say this is 5 to the power of 2x equals 5 to the power of 2. And now, because our bases are the same, we can set our exponents equal to each other and say 2x equals 2, so x equals 1. And I've solved for x here, okay? But for example, in question B right here, 5 to the power of x equals 10, 10 is not equal to 5 to some kind of an integer, right? There's no possible way for me to do 5 to some integer. So I'm gonna pull out my calculator and see what I can do with this. For starters, I don't need a calculator for this, but I know 5 to the power of 1 is 5. I also have 5 to the power of 2 is 25. So we know that x is going to be somewhere in between 1 and 2. But then we're going to use that to figure out how to get our actual answer. So now we're going to narrow it down. So let's try like 5 to the power of 1.5 and see what we get. And we get 11.18 approximately. So that's too large. So maybe I can try 5 to the power of 1.4, 1.3, and I just keep guessing and checking. Until we get closer. So watch me on the calculator. So I'll try 5 to the power of 1.4. And I get 9.5, so that's a little bit closer. So now I'll try 5 to the power of 1.45. It is a little bit closer, but too large. So I'll try maybe 1.43. It's a little bit too small, so maybe I'll do 435, and I would just keep going and going and going and going. So as we get closer and closer to our final answer right here, we our value right here is going to be like an irrational value, and we need logarithms to solve. But by guessing and checking, we can say that it's approximately equal to 1.43 something. okay? Okay, in our next example, we have different bases. Our bases are not the same, but 49 can be written as 7 to the power of 2, and 343 can be written as 7 to the power of 3. So if I multiply 7 by itself 3 times, I'll get 343. So that means right here that our common base is going to be 7. So now when I rewrite this right here, this would become 7 to the power of 2, and then that's going to be raised to the power of 3x plus 2 right here. I just keep that exponent right here. And then for this one right here, I end up getting 7 to the power of 3, and that's going to be multiplied by the exponent of 3x plus 4. And remember, when you have a power to a power, you have to multiply your exponents. So let's go ahead and multiply our exponents here. So I would get 7 to the power of 6x plus 4, just multiply that 2 through, equals 7 to the power of 9x plus 12. And now that my bases are the same, I can now set my exponents equal to each other. So now I can say 6x plus 4 equals 9x plus 12. Subtract the 6x and get 3x on this side. Subtract the 12, get negative 8 on this side. So x is negative 8/3. Okay? All right, we're going to want to do the same thing over here. Our common base is going to be 3, because 3, I can't break this down any further. But 27 is 3 to the power of 3. So here, our common base, so we're going to rewrite each one of these with that common base. I don't have to change this first term, but I'm now going to write 27 as 3 to the power of 3, and then I'm going to multiply that by 3 to the power of 2x. Now, because this is multiplication here, we're going to use the product rule, which is anything multiplied together with the same base, you can just add the exponents. So I'm going to add my exponents here, and my base is still 3, but then I can add my exponents and I get 3 to the power of 2x. And then here, I'm just going to copy this down right here. Okay, so now I can set these two equal to each other, and I can say x squared equals 3 plus 2x, subtract the 2x and the 3 over. So then I end up getting x minus 3 times x plus 1 equals 0. So that means that x equals 3 or negative 1. And those are my exponents that work here, my values of x here, okay? This next one is quite tricky. We need to do u substitution. So for starters, if you look right here, this is 2 to the power of 2x right here. So we can say that 2 to the power of 2x is the same thing as 2 to the power of 2 raised to the power of x, or it's the same thing as 2 to the power of x all raised to the power of 2, because when you multiply these exponents, you would still get 2x. So I'm actually going to rewrite this as 2 to the power of x all raised to the power of 2. And then I'm going to copy down the rest of this. Minus 5 times, I'm going to write it like this, 2 to the power of x plus 4 equals 0. So now, right here, because this is 2 to the power of x right here, I'm going to let u equal 2 to the power of x. By doing that, I now have u squared minus 5u plus 4 equals 0. See here, this is u, and then I just have squared minus 5 times u, and then plus 4. So now I can just go ahead and solve for u right here. So we'll have u minus 4, and then u minus 1 equals 0. So that means that u equals 4 or u equals 1. But don't forget to sub this back in to solve for x now. So here I'm going to say 2 to the power of x equals 4, or 2 to the power of x, get a common base is 2 to the power of 2, so x equals 2. Or I'm going to say 2 to the power of x equals 1. So 2 to the power of x is the same thing as 2 to the power of 0, because remember, anything to the power of 0 is always going to be 1. So x equals 0. Now, this next one, even though it looks like it's an exponential equation, it isn't. But just a reminder that this right here is this exponent of 1/2 means that you are going to do the square root. So 2x to the power of 1/2 is the same thing as the square root of 2x. So here I'm going to say the square root of 2x equals 2 to the power of 2. How do I undo the square rooting? I'm going to square both sides. So I'm going to square both sides right here. So I get root 2x equals 2 squared. I'm going to square both sides. And then I've got 2x is equal to 2 to the power of 4. And then I can just evaluate, right? 2x equals 2 to the power of 4 is 16. Divide by 2, I get x equals 8. Or another option that I have is to divide by 2. So then I get 2 to the power of 4 over 2. So then x equals 2 to the power of 3. Because when you divide, you subtract your exponents and you still get 8. Okay? All right, so now we're going to take a look at exponential growth and decay. Like, these are applications. And just a heads up that the general equation for exponential growth or decay is f of x is going to be equal to a times b to the power of x, okay? Where a is going to be your initial amount or your initial value. And then B is going to be your growth or decay rate. But to find B, you have to do 1 plus R, where R is the percent as a decimal. Okay, so let's take a look at an example here. So hoping to prevent extinction, we are told that we have 75 African bat-eared foxes. They were all moved to an animal reserve in Africa. The fox population increased by 15.8% each year over a 10-year period beginning in 2017. So it says to write an exponential growth function to model this relationship where P is the population and T is the time in years after 2017. Okay, cool. So generally we say f of x equals a times b to the power of x, but here we're going to use p instead of f of x and t instead of x, so it's going to be a times b to the power of t. Now, a right here is your initial value, so your initial value is 75, and then to find b, it's going to be equal to 1 plus r. Well, here, the r is equal to 15.8%, so we write this as a decimal as 0.158. So here, the b value is going to be equal to 1 plus 0.158. So b is 1.158. So putting that all together, putting all the information all together, we can now say p of t is equal to 75 is your a value, times your b value, which is 1.158, all raised to the power of t. So this is your exponential equation, okay? Then it says how many bat-eared foxes were present at the end of a 10-year period. So this is asking us to find P of 10. So to find P of 10, I'm just going to replace the t value, with 10. So when I plug that into my calculator, we should get approximately 75 times 1.158, all raised to the power of 10. We get approximately 325 foxes. Okay, so then you'd write your therefore statement, which I'm not going to have us do because of time in the video, but make sure you always add your therefore statement. Okay, in our next example, it says that a cattle farm has a population of 240 cows, but it's declining. That's really important, 3.4% each year. And then we're going to write an exponential decay function. So where P is the population and N is the number of years. So again, we always start with the general equation, which is f of t equals a times b to the power of t, but we're going to use p of n equals a times b to the power of n because it says to use p and n here. So now we know that a is still going to be that 240. It's still your initial amount, but this time b is equal to 1 plus r, just like we did before. But our r is going to be a negative 0.034 because it is declining. So b equals 1 minus 0.034. So b is equal to 0.966. So now I can fill in all that information here, and I can say that P of n is going to be equal to the A value, which is 240, times the B value, which is 0.966, and that's all going to be raised to the power of n. So this is our exponential equation right here. And then it says, what will be the expected cattle population after 5 years? So here we just need to find P of 5. So I'm going to do 240 times 0.966, all to the power of 5. And then here, I'm going to just type that into my calculator. So 240 times 0.966 to the power of 5, and we get approximately 202 cows. Okay, but again, you can get an accurate answer using logs, which we're going to learn throughout this unit. Okay, so a few more things to talk about. Half-lives. If we have half-lives right here, the general formula for half-life is going to be n equals n sub 0 times 1/2 to the power of t. Let's make this n of t, t over h, where h is your half-life. So how long it takes to cut in half. Okay, and then for doubling and tripling, it's the same idea. N of t equals n sub 0 times 2 to the power of t over d, where d is the doubling time. And then tripling would just be the same exact thing, except it would be a 3 instead. T over, let's say, P for triple time. Okay, I don't want to use T because T stands for time. I also don't want to use R because we used R for the rate. So I just don't want to confuse you with different variables. Okay, so how do we apply this? A bacterial culture began with 7,500 bacteria. So this right here is going to be your N sub 0. It's your starting amount. So actually, let's write this down, that N sub 0 is the original amount. And that's true for both half-lives and doubling time. Its growth can be modeled by using the function n of t equals 7,500 times 2 to the power of t over 36. So notice how right here, this has this 2 right here. So this means that it is doubling. But how often is it doubling? It's always doubling whatever that double time is right here. And if you look right here, that value here is 36, where t is in hours. So here, our doubling time is going to be 36 hours. So then how many bacteria are present after 36 hours? We have 2 choices. Our first choice is we could just do n of 36 equals 7,500 times 2 to the power of 36 over 36. But 36 over 36 is 1. So then 7,500 times 2 is 15,000. But if you really understand what's going on, all you have to do is know that after 36 hours, it will double once. So then your answer right here would be 7,500 times 2, which is 15,000. And again, write your therefore statement. Okay, and then the last question is, how long will it take for the bacteria to reach 3,200? So here, what we would do is we would say, well, n of t equals, we'll use the equation, 7,500 times 2 to the power of t over 36, and then I'm going to replace n of t with 3,200. And then I could use algebra to solve this, but eventually you're going to get a point where you have an exponent, a variable in the exponent, and you can only solve that algebraically with logarithms, which again, we haven't learned how to do. So our only option is to guess and check. I'm going to type in right here that we started with 7,500 times 2 to the power of, and then we'll start with 36 over 36 because we know that that will give us 15,000. That's obviously too small. So let's try another value right here. So let's try, 48. Still too small. So then let's try 72. It's still too small, but we're getting closer. So now let's try maybe 80. That is too large. So I know our answer is going to be somewhere between 72 and 80. So let's try 76. It's a little bit too high. So let's try 75. It's a little bit too low. Let's try 75.5. It's a little bit too high. 75.4, still too high. 0.3, too low. So we'll say 0.35. It's a little bit better. 0.355 is a little bit too high, so maybe 0.354, and we just keep guessing and checking and checking and checking until we get to the right answer. So we'll say it's approximately 75.35 hours. Okay, in our last example, it says radon has a half-life that can be modeled by this equation right here. So it's a half-life this time. It's modeled by this equation. We know it's a half-life because of this 1/2 right here, where t is measured in days. So it says from the equation, what's the half-life of radon? Well, in our equation, this number up here always tells us what our half-life is. So it takes 3.8 days to cut in half, okay? That's like what this equation is saying right here. Like regardless of what the original amount is, every 3.8 days, it's going to be cut in half. So if my original amount was 100, after 3.8 days, it's now going to be 50. If it's radon, okay? So it says how much of a 4 milligram sample is present after 11 days. So right here, we know that our M sub 0, our initial amount is going to be 4 milligrams. We also know that our time is 11. So here, what I'm going to do is I'm going to plug that information in. So I'm going to say M of 11 is going to equal my M sub 0, which is 4, times 1/2 to the power of 11 over my half-life, which is 3.8. That doesn't change. And then I just type that into my calculator and see what I get. So 4 times 1/2 to the power of 11 over 3.8. And my answer here is about 0.54 milligrams. And then don't forget to write your therefore statement. Okay? And then question C says, how long will it take a 400 milligram sample to decay to 25 milligrams? So let's fill in all of that information here. So we know that M of T is going to be equal to 400. No, sorry, it's going to be equal to 25. That's the final amount. We know M sub 0 is 400, and we're trying to find out what the T is. So here I'm going to say 25 equals 400 times 1/2 to the power of t over 3.8. And then I'm just going to play around with some numbers until I get there. And then I actually want to solve this one algebraically because this one turns out nicely in a way that I can actually solve it algebraically, and I'll show you how. So divide both sides by 400 and you get 1 over 16. And this is 1/2 to the power of t over 3.8. Well, 1 over 16 is the same thing as 1/2 to the power of 4. So here, now we can just set our exponents equal to each other. Multiply both sides by 3.8, and it would take 15.2 days. And don't forget your therefore statement. So that means right here that it would take 15.2 days. Let's double check to make sure this is right. So if it started off with 400, I'm going to multiply that by 1/2, raise that to the power of 15.2 over 3.8, and you definitely get 25, and this one works. How did I know that I could solve this one algebraically? I just knew, I recognized these numbers right here, and I could see, oh, I had some foresight, and I could see that definitely is going to reduce nicely with a nice common base. Okay, all right, that's it for this video. Sorry again I couldn't be there. Let me know if you have any questions.